Okay, you can use MATLAB and Octave also to find the solutions of differential equations. It doesn't find a closed form theoretical solution, but it finds will find a numerical solution to a differential equation. So let's look at the provided function. So a numerical solution would be, for a given differential equation with given initial conditions, we can use MATLAB to actually find the solution to the differential equation, the numerical solution, the corresponding curve, and actually plot that curve. Okay, there are a couple of different differential equation solvers provided in both MATLAB and Octave. I recommend starting with this ODE 45 solver. That's ordinary differential equation. The first argument is a function corresponding to the differential equation. It takes as arguments, input arguments, t, the time step, and y, the current value of the differential equation, and then it actually has to return the derivative of y with respect to t. We'll see how that's set up in just a minute. And then this next vector represents the time range over which you want to solve the differential equation. Here it's from 0 to 10 seconds. And then this last vector here is the initial conditions. And this has to be the same dimensions as actually the y vector that's passed into the your differential equation function. It will return a time vector and then the solution vector, and so you can plot t versus y. Okay, it's actually set up, and this is what makes it a little difficult to understand what's going on. It's actually set up that it solves a system of differential equations. It can be a nonlinear system, but it does have to be a system set up in a system form. We're starting out kind of with a complicated example of two coupled equations. A simpler starting point would just be a single first order differential equation. Here we've got coupled first order systems. The derivative of A depends on the current values of A and B, and likewise the derivative of B depends on the current values of A and B. So we have to write a function that represents the derivative of this system, and that's done here. It's called chem. Okay, y, the y input vector, would have as, is a two-element vector. It would have as its elements a and b, because those are the unknown variables in this system. Okay, and then it has to return dA dt and dB dt, and so the return value has to also be a two-element vector. And then we also use what's also passed in is the current time value. This set of differential equations actually doesn't depend on t on the right hand side, so it's not used here in calculating the derivative vector. But the derivative vector, the dy dt vector, needs to be the same length as the y vector, and since y has both a and b components here, dy dt has to be the same size, and that's a common mistake, to try and make dy dt just a single value. So here's how you would use that now to actually solve that. We pass the function name. Again, you can use the at notation. We're integrating from 0 to 0.5 with these initial conditions. And then what we get back here is we'll get the A solution vector will be in the first column of y. The B solution vector will be in the second column of y. And then we can plot those versus t. So we're plotting A in black and B in red. When you look at that, this is what the solution to that differential equation looks like with these initial conditions, starting with the initial conditions where A is equal to 0 and B is equal to 1. And we see that, A is the black line, it starts out at 0, and then B is the red line, it starts out at 1. You can use this to solve nonlinear differential equations, but Octave requires that for an arbitrary order differential equation, you have to convert it into a system of first order equations. And there's a technique for doing that. That's illustrated here. You have to introduce a dummy variable or dummy variables for the higher order derivatives. I'm not going to go through the process. I'll describe it briefly. Here's a second order differential equation describing the angle of a pendulum and how its acceleration, the angular acceleration, depends on the current sign of the angle, the gravitational constant, and then the pendulum length. So we can solve this for a second derivative, but again, our ODE solvers only work with first derivative. So we just introduce a dummy variable, let the first derivative here be gamma, and then so in this case now we can rewrite the second derivative equation as in terms of a derivative of gamma, and then we also have theta dot equal to gamma, and then gamma dot now equal to the right hand side here. So what our vector now will actually consist of two elements. Our solution vector will consist of theta and gamma elements. And so when that's passed in along with the time variable, again, the differential equation here doesn't depend on time, we have to return a two-element derivative vector. So what's passed in here, the first element is theta, the second element is gamma. We see that the derivative of theta of the first element is just gamma. So we could simplify this a lot. You could just let dx dt be equal to gamma, and dx dt, the second element, has got to be the derivative of gamma, which is theta double dot, and that's just minus g over L times the sine of the x1. So, but this is kind of showing that kind of expand. You could certainly write this function a lot more concisely. And you call it, we're integrating from 0 to 10 using these initial conditions for theta, and this is gamma theta dot, and then we plot those. So we're plotting, this is in blue is theta, and then theta dot, the angular velocity, is shown in red. That's the second column here from our solution vector, and we plot those versus t. So this is showing a plot of the angle of the pendulum and the angle of the pendulum and the velocity of the pendulum as a function of time. You can also plot the angle versus velocity. That's known as a phase plot. This has some interesting information here. You can see when it reaches the extreme angular positions of, this would be like about minus pi and plus pi in the positions here. That's when the velocity is actually equal to 0. And then it reaches the minimum maximum velocity at an angular position of 0. Okay. The velocity here is when it's positive, when it's actually moving in one direction, counterclockwise, and it would be negative when it's actually moving in the swinging back in the other direction. Okay. You can provide a lot of custom options to the ODE solvers. Here's an exercise on using this. You can try this if you want. You can pause the video. I'll show you, and here's the result. Here's how you would solve it. Again, this is fairly complicated. I'm not going to assign any homework that requires you to solve these differential equations, although I will put it as one of the optional problems if you want to attempt this, because this requires a little bit more MATLAB wizardry than I want to get into in this course.